Good afternoon, everyone. I am Mukesh Mishra, your chemistry faculty at Aakash, and today I am going to discuss about the AIATS plus phase 2 questions for mock test 4th. So basically I will be dealing with GOC part, hydrocarbon parts, and haloalkanes and haloarenes part. Okay, so these questions will be discussed by me. You might be aware that there are various faculties which are continuously supporting you with the questions of other chapters also. So you should attend all the sessions and you should definitely note down each and every concept which I discussed during the class, okay, so that you can revise it later on. Is this clear to all? So now let's proceed with the first question. Good morning, Ishani. So now let's come to the first question. So I am from class 11th. Okay. Major product of the reaction is, so here we have been given CH3, CH, CH3, CH double bond CH2 plus HCl. Now this reaction utilizes a very important concept of class 11th, and you all should be aware of that. So that this concept is basically electrophilic addition reaction of alkenes, and I am going to discuss that concept in detail, and then we will come back to the question. Okay. So now let's talk about electrophilic addition in alkenes. So this is a very important concept. Okay. So first of all, I will be taking a very simple alkene to explain, what is the phenomena that is involved here. So first of all, let us take a very simple alkene, that is propene. CH3, CH, double bond, CH2, and now when it is allowed to react with HCl, we have to find out what will be the product that will be formed. Good afternoon, Anjali. Okay. So now, first of all, the basic step which is required here is generation of an electrophile, and you all know that electrophiles are electron-loving species. Okay. And in alkenes, if you talk about this carbon and this carbon, these two are sp2 hybridized. Okay. And they have one pi bond, and the pi bonds are therefore, sideways overlapping. So if I draw a pi bond here, so you will find that these carbons will have pi bond, pi overlapping, side overlapping will be there, and this pi bond is basically exposed. Okay, and due to this exposure, it becomes easier. Okay, it becomes easier for the electrophile to attack at this point. Is this clear to all of you? Yes, Rahul Helaut, we are going to discuss all that things in detail. Don't worry about that. So first of all, the first important step is generation of an electrophile. Electrophiles are basically the positively charged species or electron deficient species. So HCl will produce an electrophile. So how an electrophile will be produced here? First step is HCl dissociates to give H plus and Cl minus. Now see, you can see here that this carbon, have pi electrons which are above the plane. So out of this H plus and Cl minus, which will be acting as an electrophile? Yes, write in the comment section. Which has more tendency to get attracted towards electron? Definitely the one having the positive charge. Yes or no? Good afternoon, Xenia. So definitely this H plus will, come to this, will attack this center. And how this attack will take place? You have to understand here. CH3, CH, double bond, CH2. And if H plus is there, this step is very important. Now you can see this double bond, pi electrons, they have, two form. These pi electrons will definitely move towards this H plus. And because of this, this hydrogen has two options. It has two probability. Either it can form bond with this second carbon, and it can also have form bond with, this first carbon. So let's see all these things here. Your question is not clear, Sumit. You have written isoelectronic species or electromagnetic species, electron loving species. Write down clearly that what you want to ask. I will definitely clarify that out. Now come back here and see, two possibilities are there. If this pi electrons remains with the second carbon, then what will happen? The hydrogen will form bond here and CH2, and this plus will be formed. Carbocation is being formed. Okay. Now another probability is that this hydrogen or this double bond, pi bond remains with this carbon, and due to this what will happen? CH3. This carbocation will be formed. Now you can see this is your 1 degree carbocation, and this is 2 degree carbocation. So can any one of you tell that which one will be major product here? Because this step will determine that what will be the final product in major quantity which we are going to obtain. So if you look at carefully, you will find that this 1 degree carbocation has only 2 hyperconjugates. But this 2 degree carbocation has 6 hyperconjugation. So if you are following my lectures from the starting, in previous lectures I have also discussed about the carbocations and their stability, and we have discussed that hyperconjugation actually helps in the stabilizing the carbocations. Okay. So this carbocation is more stable. While this carbocation is less stable. So definitely the product that will be formed here will be the one which is having the more or maximum or higher stability. So definitely this will be formed in major amount. Okay. So this 2 degree carbocation will be generated in major amount. Exactly, Rahul. So let's have a look here. That if 2 degree carbocation formed is more, then the third step is still after the attack of H plus, we have this Cl minus. This Cl minus in the next step will form bond with this carbocation, second 2 degree carbocation, and we will obtain the product. So in third step, we have, I am taking only the major product. Okay, plus Cl minus, and it will form CH3, CH, Cl, CH3. This will be formed here. Similarly, minor product will also be formed here. Now this rule is basically called Markovnikov addition. Okay, because in Markovnikov addition, the negative addendum is added to that carbon which has lesser number of hydrogen. In other words, you all have memorized it, that rich gets richer. That the carbon having more number of hydrogen will receive more hydrogen. Is this clear? So this is basically governed by a very important rule, that is Markovnikov rule. Okay, means negative addendum is added to that carbon which has lesser number of hydrogen. This is how we, but the reason for this is because of the stability of carbocation is the main factor which decides the product obtained. So this step is very important. Is this clear to all of you? Now we will learn certain exceptions and then again we will come back to our question. So this is how this reaction takes place. This electrophilic addition takes place. In hydration also we are going to follow the same rule, because you can see here in the question we have HCl, and HCl, the negative addentum is Cl minus. So Cl minus in major product is getting attached to the carbon that is having the lesser number of hydrogen, because in the initial reactant also you can see here that it has only one hydrogen. Is this clear to all of you? So there is anti-Markovnikov addition also, that also I am going to discuss. Till then you can note down this, and let's come back to the question again. Now let's have a look to the question. So the major product of the reaction is we have CH3CH, CH3CH double bond and CH2 and HCl. Now you might be thinking that, sir, if this H plus will attack at this pi bond, then there are two possibilities. Okay, the more stable one is the one with positive charge here. But one thing you have to keep in mind here, that still carbocations have ability to undergo rearrangement and they can form more stable carbocations. So if this possibility is there, then definitely carbocation will utilize that property. Now you can see here a very important concept is there. Suppose CH3, CH, CH3 is there, and if the H plus is getting attached to this terminal carbon, it will become CH3 and positive charge will be there. Okay. In one look, it appears that okay, this will be the major carbocation that will be formed here. But after the formation of this carbocation, still a rearrangement is possible. Okay. And what will happen, that this hydrogen which is present here, what it will undergo? It will undergo rearrangement. This H bond will move here, and what we will finally obtain, that is CH3, C, this positive, and CH3, again CH2 and CH3. So this will be the major carbocation which we are going to obtain. Exactly, Rahul. And the product will, and this method will be called as hydride shift, because shift of hydrogen is taking place. Is this clear? So here you can see that after this, the Cl minus will attack at this carbon, and the product obtained will be CH3, C, Cl, CH3, CH2, CH3. So this is the major product that we are going to obtain. Hence, option 3 will be the correct answer. Anyone having any doubt? Feel free to ask. No doubt. I will show you one more very interesting example of this case, where instead of hydride, in fact, the whole methyl group gets transferred. So let's have a look here. Suppose okay, we have this CH3, C, CH3, CH3, CH, double bond, CH2. If this is the compound which is undergoing reaction with HCl, okay, then what will happen? You have to understand here. First of all, again, we have discussed that important step is stability of carbocation, and you know that by the addition of this H plus, the more stable carbocation, first the carbocation that will be generated will be CH3, C, CH3, this carbocation will be generated, but this carbocation will again undergo rearrangement, because it has possibility that if this CH3 group moves to this place, then what will happen? This is called methyl shift. And due to this methyl shift, we are going to obtain a more stable 3-degree carbocation. CH3, C, this will be CH3 again and CH3 here. So methyl shift is taking place, and yes, Rahul, we call it as methyl shift. And now again this Cl minus will react, and the product obtained will be CH3C, CH3, Cl, CH, CH3, CH3. So this will be the product that we are going to get. So you can note down this, these are exceptional cases. Now, again, in the electrophilic addition of alkene, there is one more very important example, one more very important reaction, that is called peroxide effect or Kharash effect, that follows the mechanism of free radical addition. So I am going to discuss that too also. So as we have discussed the Markovnikov rule, now we are going to discuss the anti-Markovnikov addition. Suppose okay, now we have this CH3, CH double bond, CH2, and we have HBr in presence of benzoyl peroxide. Okay, then what will be the product obtained here? Okay, now we have to find out. Now here what is going to happen, this peroxide, will help in the regeneration of, or will help in the generation of free radicals. Okay, you can see here that first of all, this benzoyl peroxide, C6H5, C double bond O, C6H5. Again, you can see here, this will undergo homolytic cleavage. Okay, and let me tell you one thing, that if first step of the reaction is homolytic, then other reactions, other mechanism, other part of the same reaction will also follow the homolytic cleavage. And due to this homolytic cleavage, you will be getting first of all 2 moles of C6H5, C double bond O, okay. And now again, after this what will happen? This free radical is there, homolytic cleavage of this will also take place, and finally you will get 2 molecules of C6H5 free radical plus 2 molecules of carbon dioxide. Now this will act as a free radical, and again it will help in the formation of other products also. Now what will happen here? This C6H5 free radical will react with HBr. So again, what is going to happen here? We have discussed that if the first reaction is, if the first step has homolytic cleavage, then in the mechanism other steps will also follow the homolytic cleavage. So here homolytic cleavage will take place. Okay. Now what will happen after this homolytic cleavage? Again, you have to understand here, there are 2 possibilities. This hydrogen free radical will be produced and this Br free radical will be produced. 2 different free radicals are there. And out of these 2 free radicals, it has been observed that always this hydrogen free radical will form bond with benzene. Okay. So what is going to happen here? This C6H6 plus Br free radical. Now this Br free radical will follow the further steps in the mechanism. You can see in second step CH3, CH double bond CH2. Now this Br free radical will be there. Again homolytic cleavage. Okay, and due to this homolytic cleavage, what you will find out that again 2 possibilities are there. CH3, CH, free radical will be here, and CH2, Br will be formed. Okay, and again other possibility is that CH3, CH, Br, CH2, free radical. Here you can see that it has 1 degree free radical. It is 2 degree free radical. So out of 1 degree and 2 degree free radical, we have discussed that actually the 2 degree free radical is more stable. Okay, same because of the effect of hyperconjugation. We have discussed in our previous lectures also, or you can, if you have any doubt, you can go back to my previous lectures, or you can go back to the playlist on Aakash. There you will find GOC ka Taaz Organic Peraz by Pankaj sir, and in that also you will find that this hyperconjugation, it has been discussed that why 2 degree free radicals are more stable. So this one is 2 degree, this one is 1 degree, this is more stable, and as it is more stable, this will be formed in major, as a major compound. Is this clear? So the next step out of this, again you will find that CH3, CH free radical, CH2Br, again it will react with HBr, and again homolytic cleavage will take place, and it will form CH3, CH2, CH2Br. So this is how, the Br will be added to Sir, this anti-Markovnikov is going through free radical mechanism. So can here be disproportionation product can be obtained like Wood's reaction? See, generally you can say that there will be many product in free radical mechanism, but you have to look for the most or the major product which are being produced. Okay, so major product will follow this mechanism only, and it has been observed through practical. See, theoretically again we are talking about that different type of products can be obtained, that sir this Br can react with C6H5 also. Okay, in 1% case or in 0.1% case this will also happen, but 100% most of the time, in fact more than 95% of time, it has been observed that this H will form with bond with this C6H6. Okay, so it depends on the thermodynamics of the reaction also. So in this case, it has been observed that major product is not disproportionate product. Most major product is from this mechanism only. But yes, your 200% pure product can't be obtained. Okay. So again you can see here that anti-Markovnikov addition has taken place. Is this clear to all of you? So you can see here the product which we have discussed. This is how the reaction works. So we have discussed a simple case, CH3, CH double bond CH2. If it simply reacts with HBr, and another case is that HBr reacts with in presence of peroxide. It can be benzoyl peroxide, hydrogen peroxide, or other free radical generators. Okay, so you can use any of them. So in that case, what is going to happen here? That in this case, Markovnikov addition will follow, due to which the product will be, major product will be CH3, CH, Br, single bond, CH3. Okay, but in this case, because of peroxide, free radical mechanism will follow, and anti-Markovnikov product will be obtained, CH3, CH2, CH2, and Br is also here. So this will be the product obtained, So they are totally inverse. Now one more very important thing you have to understand, that this peroxide effects works only for HBr. It does not work for HCl, and it does not work for HI also. The reason for this is, because the bond strength in case of HCl is more as compared to HBr, and the free radical does not have that much of energy to break those bond. Okay, and in case of HI, the bond strength is very less, and generally it has been found that iodine free radical join with each other to form iodine, I2. Okay, so therefore These two, only Markovnikov and anti-Markovnikov, two opposite reactions are possible only with HBr, okay, not with other HCl or HI. Okay, Asif? Anything else you want to know? So this is how. So now you have to understand that in the addition reaction of alkene, you have to take into account for whether it is going for Markovnikov addition, whether it is going for anti-Markovnikov addition, okay, or you have to also think that if carbocation is being formed in the reaction mechanism, then is the rearrangement possible? Is it advantageous for the carbocation to become more stable after stabilizing, after rearrangement? Then that will be the major product. So I have discussed most of the thing here. Is this clear to all of you? Anyone having any doubt? Feel free to ask. And one more thing, rearrangement does not take place in in free radicals. This point you also have to remember. Okay, now let's move on to the next question. So this is how we'll proceed. Now, next question is also a very interesting one. On the reductive ozonolysis of CH3CH double bond C CH3CH 2CH3, one of the product obtained is. So you have to think about ozonolysis here, okay? And let me tell you one thing, ozonolysis is of two types, reductive ozonolysis and oxidative ozonolysis, okay? I will tell you the difference between both of them, don't worry about that. First of all, we are talking about reductive ozonolysis. During reductive ozonolysis, what will happen? That O3 will be used first, and in second step, we are going to use Zn plus H2O. Okay? NEET-25 is saying, sir, 222 is the correct answer. I am not going to discuss answer right now, don't worry. But first of all, let us understand the difference between reductive ozonolysis and oxidative ozonolysis. So second one is ethanol only. Yes, you have written methanol first. Okay. Now, another one is oxidative ozonolysis. During oxidative ozonolysis, what is going to happen here? That in first step, again, we are going to use O3, but in second step, we use Zn H2O2. Peroxide is being used here. Now, what's the difference? Is there any difference in the product which we are going to obtain once we use these two different, reagent? That I am going to discuss here. Now, suppose I take a very simple example here. CH3 again, propene, a very common example. First of all, it will react with ozone to form a ozonoid structure. And what is this ozonoid structure look like? CH3, CH, O. Okay, this is how this look like. Now, once you add zinc and H2O, in presence of zinc and H2O, cleavage will take place like this. And what we are going to get, see, zinc ZNO will be react with this oxygen, you will get ZNO, okay. Again, you will find here that CH3, CHO will be formed, plus, again, you can see HCHO. So these oxygen will form double bond with the carbon. Exactly, Rahul. You have written the correct thing, which I am going to discuss now. But see, if, anyhow, we are going to use, suppose, if we are talking about oxidative ozonolysis, CH3, CH, double bond, CH, CH3. Suppose we are carrying out the oxidative ozonolysis of this compound. Okay, then what will happen? First of all, it will react with ozone to form ozonoid structure. Okay, and once it is allowed to react with ZnH2O2, means oxidative ozonolysis. Now what will happen during oxidative ozonolysis? If any of the product formed during ozonolysis is aldehyde, then that is oxidized to, carboxylic acid. But if a product formed in the oxidative reductive ozonolysis is a ketone, then you all know that ketone can be or cannot be oxidized further easily without breaking the carbon-carbon bond. Therefore, if aldehyde is being formed as a product of reductive ozonolysis, in that compound, if oxidative ozonolysis takes place, so instead of aldehyde, a carboxylic acid will be produced. Is this clear? So, if this react with them, ZnH2O2 is here, and final product, instead of this aldehyde, we will be obtaining 2 molecules of CH3COOH. I hope this thing is clear to all of you, the difference between reductive and oxidative ozonolysis. Now, let's come back to our question. In examination, you just have to focus on the carbon-carbon double bond. In exam, just break these 2 double bonds and add double bond O, you will obtain the product of, ozonolysis. Okay? If hydrogen is there, then definitely you will get 1 aldehyde. If this hydrogen is also substituted with R, then you will get ketone. Okay? In oxidative ozonolysis, if 1 hydrogen is present, then after the cleavage of this carbon-carbon double bond, what you will get? That will be further, the aldehyde formed will be further oxidized to carboxylic acid. Okay? So, in examination, they can ask questions in many ways, that they either you carry out the ozonolysis for the given substance, or they can give you the product, 2 carbonyl compounds which are obtained, and you have to find out from which alkene you are going to get those final product. Is this clear to all of you? Okay, now let's come back to the question first. You can see here the reductive ozonolysis of CH3CH double bond C CH2CH3. One of the product obtained is. Now, I have just told you that you just have to apply a shortcut method here. Okay, just break these 2 bonds, and instead of them, NEET-2025 question asked on same concept. Exactly. So, just break these 2 bonds and and form CH3CH double bond O. So, this is an aldehyde plus, again what we are going to get? We are going to get C double bond O, CH3, CH2, CH3. So, these are the 2 products which we are going to get. Now, let's have a look. One of the product obtained is CH3CH2OH. Alcohol can't be formed. Okay. So, this one is straightforward wrong. CH3CHO, this is here, and this should be the correct answer. Let's have a look. CH3CH2CHO, no, this is not there. And again, in ketone, we are not going to get propanone. Okay. No, ऑक्सीडेटिव में कीटोन COH में नहीं होगा, क्योंकि उतनी ज़्यादा बॉन्ड, उसमें काफ़ी ज़्यादा पावर, मतलब इतनी जल्दी आसानी से हम कार्बन कार्बन बॉन्ड को ब्रेक नहीं कर पाते. कीटोन का ऑक्सीडेशन इट इज़ अ लिटिल बिट टफ. So only aldehyde converts to carboxylic acid. So this thing is also, this product will also not be obtained, and this will also not be obtained. So correct answer is option number 2. Anyone having any doubt? Now you can imagine any compound which has C double bond C in between them, and you can go for the product formation. So for example, if I take a benzene, and if benzene is allowed to undergo reductive ozonolysis or simply ozonolysis, then what will be the product formed here? Can any one of you tell? We have benzene. And first of all, if it is, allowed to react with ozone. Second, zinc H2O. Yes. What will be the product formed here? So there are 3 double bonds, and all the 3 double bonds will actually go for formation of ozonoid structure. This structure which I have drawn here is ozonoid structure. Okay, and after this formation of this ozonoid bond, again it will form double bond O. So what will happen? You can see here that cleavage will take place at 3 positions. Okay, and I have told you that remove this double bond and add double bond O. So you can see you will be getting 2 carbon with each other. So first product will be C, one H is there, double bond O, C, H, double bond O. See, all the carbon of benzene contains 1 hydrogen. So similarly, again, this will also give the same 2 molecule, this will also give the same molecule. So 3 molecules of what you are going to get this. So they are actually CHO, glyoxal. So 3 molecules of glyoxal will be obtained. So this is the product that will be formed here. Anyone having any doubt? Feel free to ask. See, the compound, looks much bigger that, if you have to make ozonoid structure, then it will be difficult to solve. So that is not the case. Okay, you just have to cleave the double bond, C double bond C, and again add double bond O instead of in the both the carbon which are there. Okay, now one more simple thing I am going to ask you, that instead of ozonolysis, can you, any one of you, tell that where you have seen the cleavage of C double bond C? What are the reagent which you can use to cleave the C double bond C? A very strong oxidizing agent is there. That is KMNO4. Okay, so KMNO4 also cleaves the carbon-carbon double bond. Okay, that also acts as an oxidizing agent. Now let's move on to the next question. Next question is, yes Rahul, KMNO4 is the correct answer. 0.1 gram of an organic compound gives 0.233 gram of barium sulfate. The percentage of sulfur in the compound is exactly acidic KMNO4. See, this we have discussed in Carious method in my last session, and I hope all of you must be remembering that the formula which I have used, how unitary method is useful in solving such questions. Now have a look back again here. See, 0.1, suppose we have taken a 0.1 gram of an organic compound. Okay, and we have precipitated barium sulfate. Okay, we pass fuming H2SO4 and then barium, the sulfate, so that you will get this barium sulfate. It precipitates, and from this 0.1 gram of organic compound, 0.233 gram of barium sulfate has precipitated. It simply means that all the sulfur that was present in this 0.1 gram of organic compound has now moved in this barium sulfate. So the amount of sulfur that is present in this 0.1 gram organic compound is same as that of the sulfur which is actually present in barium sulfate. So we all know that molecular mass of barium sulfate is 233 gram and sulfur has mass of 32 gram. So from this, Kumaran is saying 32% will be the answer. Let's have a look here. 233 gram of barium sulfate has sulfur that is equal to 32 gram. Okay, Inakshi. Now have a look here. 1 gram, simply unitary method you have to apply. Barium sulfate has sulfur equal to 32 by 233 gram. Okay. Now what you have to do, that instead of 1 gram we have actually 0.233 gram of barium sulfate. So this 0.233 gram of barium sulfate has sulfur, that is 32 by 233 into 0.233. Is this clear? Now, this is the actual amount of sulfur which is present in this 0.1 gram of organic compound. So what formula we have to use to find out the percentage? The mass of sulfur that is there in organic compound divided by, total mass of the organic compound multiplied by 100. So percentage of sulfur equal to mass of sulfur in the organic compound, that is 32 into 0.233 by 233, yes, and divided by 0.1, which is the actual mass of the organic compound which was there, into 100. Okay, on solving this, this you will get 1000. Okay, this 1000, it multiplies with 0.1, becomes 100, and this all will cancel out, and the correct answer will be 32%. Okay, this is how you have to solve these questions, and option 4th will be the correct answer. Anyone having any doubt? Feel free to ask. Okay, so this was the question here. Now let's move on to the next question. Most stable carbon ion among the following is? Rahul Helawat is saying, sir, please also tell heat of hydrogenation. See, if you go back to my class, which was there on, if you go back to the live sessions of Aakash, there you will find a topic with heat of hydrogenation. Okay, I think it was 3 weeks ahead. So there I have taught the whole concept of heat of hydrogenation. You can watch my video after the session. Okay? Okay, Rahul? So in the next class, I will ask question from heat of hydrogenation also. So be prepared. Now, most stable carbon ion among the following is CH3CH2 minus, CH3CH minus, CH3CH3 minus. See, in the last session, some of the students, we were actually discussing about the stability of. Inakshi is saying, sir, option number 4th is correct. Can any one of you tell that why this option number 4th is correct? Why, Inakshi? Why you think that option number 4th is the correct one? See, we have certain stabilizing forces, and in order to increase the stability, we have to look for the lesser amount of charge. Okay, resonance, hyperconjugation, or inductive effect. Inductive effect can also stabilize and can destabilize also. 3 degree. Okay. Now let's have a look here. Most stable carbon ion among the following is. Now Inakshi is saying that, sir, option number 4th is correct because it is 3 degree. But that is not the case here. You have to understand the concept very well here, that stabilizing forces are hyperconjugation and resonance. Both of them are not applicable here. Okay, because for hyperconjugation to take place, see, resonance you can understand that alternate conjugation is there. Okay, no, 3 degree is not the most stable one, Inakshi. Okay, for hyperconjugation to take place, it is very essential that there should be an empty p orbital, sp2 hybridized carbon should be there. It should be either where sigma to pi or pi transfer can take place. But here what will happen, that there is no empty space. So definitely hyperconjugation is not going to work here. Resonance also is not going to work here. But you can see that inductive effect is there. And inductive effect of this CH3 Pragati actually increases the negative charge on the carbon ion. And because of this negative charge, because of this plus I effect, the electron density, exactly, methyl have plus I power. So they can donate electron and can increase the electron density here. And due to this electron density, the net charge here is maximum. So this one is the least stable. Okay, and maximum stability is for CH3 minus. Okay, because it has only hydrogen, no extra alkyl group is there to donate electrons or to increase the negative charge. That's why this one is most stable, and this is the correct answer for our question. Exactly, yes. So that is the concept which you have to apply here. Now let's move on to the next question. Question number 57, a very important question. CH3 C's triple bond C and CH3. It is allowed to react with sodium in presence of liquid ammonia, then hydrogen in presence of palladium, charcoal, and which has been poisoned with some sulfur compound or quinoline, etc. So we have to understand here that during this situation, what is going to happen, that hydrogen molecule will be added to this alkyne, and this hydrogen molecule after addition will produce cis butene 2-ene in one case and trans but 2-ene in another case. So if I talk about this, sodium in presence of liquid ammonia, it forms C double bond C, CH3, H, H, CH3. So this is trans, yes, this one is A and this is trans but 2-ene. Okay, but in case of B, what it is going to deliver? This is cis. So they are basically geometrical isomers of each other. Okay, and can any one of you tell the common name of this catalyst? Hydrogen in presence of, exactly, Inakshi. Option number 1, exactly, Rahul. Option number 1 is the correct answer here. And this catalyst is called Lindlar's catalyst. Yes, study Empire. Now, let's move on to the next question. The correct IUPAC name of the compound is, so we have this compound. Exactly, Rahul. Lindlar's catalyst, B is. So the correct IUPAC name of the compound. Now here you have to think that from where the numbering should be done. Okay, basically for the IUPAC nomenclature we require word root, suffix and prefix. Okay, so basically word root decides our number of carbon in the parent chain, and you can see here that as 6 carbon are there in the ring, so definitely this will be considered as our parent molecule. So we have cyclohexane there, as it is cyclic, so we have cyclohexane. So this is the mixture of word root plus suffix, because alkane it has single bond only, so it will be taken as suffix. But now we have to think about prefix, and for prefix numbering is the most essential part. Okay, numbering and the arrangement. So first of all, there are two possibilities. We always go for lowest locant rule. So either I can choose this carbon as 1, 2 or 3, or I have one more possibility. See, 1, 2, 3, 4, 5, definitely it will not be there, because again it will not be the most proper form of numbering. Or you can even think that, sir, we can take 1, 2, 3. Now try to understand that on the first carbon, we have 2 substituent. So here actual numbering is 1, 1, 3. And here the actual numbering is 1, 3, 3. Because if you name these 3 and 3, then you have to write in the nomenclature 3, 3. So definitely, from lowest locant rule, we have to cancel out this type of numbering. So this one is wrong. Now, you can see here that you have two suffixes. One is dimethyl and another is ethyl. Okay. At first position you have dimethyl and on third position you have ethyl. But again there is one more very important rule, that while writing the prefixes you have to follow the numerical. Yes, you have to follow the the alphabetical order. Again, some student might ask, sir, in dimethyl D comes first, so whether we have to consider that or not. So you have to think, Purvi, that we don't have to take the numerical prefixes in there while considering the alphabetical order, because prefixes, substituents are methyl and ethyl. Their number may vary. So out of ethyl and methyl, ethyl comes alphabetically first. So therefore we have to write 3 ethyl first, then 1, 1 means all the locants has to be mentioned. Okay, 1, 1 dimethyl, and in continuation you have to write cyclohexane. Okay, so the correct answer here is option number 2, 3 ethyl 1, 1. Yes, Purvi, 3 ethyl 1, 1 cyclohexane. Anyone having any doubt in this question? Now let's move on to the next question. In the given reaction, the major product A is, so this is the question from haloalkanes and haloarenes. See, Mg in presence of ether, if you allow to react this in first step, it is diethyl ether. So what will be the product formed? We are going to get MgCl, and RMgX, we call it as Grignard reagent. Yes or no? Now, you all know that Grignard reagent reacts with H2O, okay, or in water. It actually gives back the alkane molecule. So you are going to get this cyclohexane, okay, plus MgOHCl. So the product that we are going to get is definitely option number 2. Anyone having any doubt? See, this is the reason, this second reaction which we have discussed, that in presence of water the Grignard reagent gives, very good Hridyansh, gives back the alkane to us. So that's the reason why we don't expose the Grignard reagent to the atmosphere. We have to keep it in a dry place, because if it is exposed to atmosphere, water vapors are there, it will definitely react with them and convert to the alkane. Okay, Kankar? Anyone having any doubt, feel free to ask. Yes, Kankar, what do you want me to repeat? First step, this is magnesium plus ether, MgCl. It will form Grignard reagents. This is the simple reaction, that how from haloalkanes, when they are allowed to react with magnesium, they form the Grignard reagent, RMgX. E2O, ethyl O ethyl, that is diethyl ether. Again, for the reaction of Grignard reagent, you can't use ether. You can't use water or proton donors, because again they will convert back to the cycloalkanes or the alkanes. Is this clear, Rahul? That is the basic concept here. E2 stands for ethyl, diethyl ether is there. Or you can use any ether also. Anyone having any doubt? Yes, dry ether we have to use, because if water is there, again we have to keep the Grignard reagent in cool place. Otherwise, it will very easily, very fastly convert to alkane. That is the second one is the proof here. Okay, so this was all from my side. Okay, you have other teachers coming with other lectures also, so you should definitely join them. And till then, take care and have a nice day, everyone.